Okay, everybody, welcome to the last lecture of Psych 2301. So it's flown by, and I will say I am pleasantly surprised at how much I've enjoyed teaching this class. I won't presume that you're pleasantly surprised at how enjoyable the class has been, but if you haven't, please hand in your paper in the pile here. Okay. Just 2 chapters left. We'll finish both today. I'll remind you at the end, next week is optional test review. Some people were asking what that'll look like. It's basically office hours, but with everyone here. I will just say, are there any questions? If there are no questions, I'll sit down and wait for them. That's what will happen next week, so totally optional. You can bring your questions then. And then the final, unfortunately, is in a while. It's on the 18th. If it were up to me, I would have the test next week, but I'm not allowed to have a test that's worth more than 15% within the last 2 weeks.
Is that college policy?
It's a college policy.
I was about to say, can we lie and do it anyway?
I'm on probation, so maybe after 2 years, I get the functional equivalent of tenure, where I have to murder someone on live TV to lose my job, basically. But I'm not there yet. So for now, I'm gonna follow all the rules.
God damn it.
Yep.
What if you made it worth 14% and then an extra 1%?
No, it has to be on anything over 10. So
So
if,
10% and then make 5% in other papers.
yeah, I could do that, but I'm not going to. It's an interesting idea. Now, I should say, the reason for that is, it feels nice for any particular class to do it that way, but then if every class does it on the last week like they'd like to, you have 4 finals on the last week. So that's the reason for the rule. It's one of those things where, yeah, if you let one prof do it, it's not the end of the world, but if everyone does it, then your life's suck. So.
Yeah, but I mean, I have 3 finals in the first week of finals week anyway, so.
Yeah, but at least you don't have lectures too. There's not new info to learn.
Oh,
We do that democracy vote thing.
For this? No. This, with regard to this topic, it is a dictatorship. So, anyways, okay. So let's do chapter 14. So chapter 14 is the statistics chapter. I mean, there's been little bits here and there of statistics throughout the course, but this chapter is all on statistics. If you've taken 2300, most of this should be review. Not really much math involved, more treating the statistical concepts at a zoomed out conceptual level. In a prior chapter, we talked about the 4 different scales of measurement. So just to review, they are nominal, ordinal, interval, and ratio. So quick review, nominal are the ones where it's just a name. That's what the word nominal means. So things like gender, ethnicity, what's your favorite movie? Just close the door. So there's really no mathematical content. It's just there may be a number in the data set, but they're just labels that are slapped on to people. Or, as I mentioned in that earlier chapter, these are in order of mathiness. The more further down you go, the more mathy they are. Ordinal, you have the greater than, less than relation. So, one is more than another, but there are not equal intervals. The gaps between the numbers are not necessarily equal in size. For interval, the intervals are equal in size, but what you lack is a true 0, where 0 in the scale means the absence of the thing. Once you get that, then you've graduated into ratio. If you have a true 0 and all the other stuff, then it's a ratio scale. These last 2 are continuous, and the first 2 are categorical. Continuous is more important to know. I don't think it's listed in the key terms, is it? But it'll just be relevant for some of the distinctions with different kinds of graphs we'll be talking about.
Is categorical a synonym for the word discrete in this case?
Yes.
Copy. Sorry, there's that.
You're forgiven. So yeah, but some graphs we'll be talking about you should only do if it's a continuous variable. So a very common graphical representation in psychology is the frequency distribution. There are various ways of representing frequency. So just as a simple example, suppose we want to represent the frequency of different grades. So let's say F, D, A. Let's say there's, and we'll include in this, A minus, A plus. So the x-axis is the different scores or values you can have. And then the y-axis is how frequent are each of those values? How many people are there at each of those values? So, so there's 1 here, it's a small class. 4 here, right? So each bar represents how many people there are at that value. So now, strictly speaking, this is one way of representing a frequency distribution, namely a bar graph. So if there are bars, it's a bar graph. So this should be a review from, I don't know, grade
Great.
8.
What's your
grade
one
8.
sentence definition for a frequency distribution?
A representation of how many people are at each value.
Sure.
So so it's very good when you're looking at data to give yourself some kind of visualization of the frequency distribution. And there's a few reasons. One that the book mentions is you can see outliers more clearly. If you just look at the data set, you can't really tell, but let's say that, and this is actually probably roughly what this class looks like. If it looks something like this, the people who are at F are outliers. Most people are here. There's a few extreme values over here, right? So, and that might be relevant to which kinds of analyses you use. I'll review this later. You probably heard this in intro psych. This is important for choosing which measure of central tendency you use. For example, the mean, which is the most commonly used, the mean is very sensitive to outliers. I'll be talking about that later.
Cool. What's your one sentence definition of the term outliers?
You can say there's extreme values or people with scores that are very far from most others.
That are there. That's great. Okay. What's your one sentence definition of bar graph?
Okay, well, a representation of the frequency distribution that includes bars.
Sure.
That are not touching.
So technically the histogram is a type of bar graph, but if it's not clarified, then I guess assume that they're not touching. So a term that's coming up is histogram. With a histogram, that's a type of bar graph where they are touching. Yeah.
Repeat the description one more time.
For a bar graph?
Yeah.
Just a representation of a frequency distribution that includes bars, like these. I think I mentioned in a prior class, you can draw it on the key terms. Include some words like this or I don't know, like something, but if you include a drawing to help gesture at the definition, that's fine. A different way of representing frequencies, which is very rarely used in psych, but you might as well know the term. In fact, most of you probably do know the term, pie chart, right? So, you have a circle and then the slices represent, how many people have a particular value. So you'd label the slices.
And what's your one sentence definition?
one sentence definition, a circle graph with slices that correspond to frequency.
Cool. Circle graph with slices that correspond to frequency. Slices.
Doesn't it represent them as percentages though on a pie chart?
Oh, that's true. So yeah, well, not always, but yeah, often it'll be represented in terms of percentages.
Frequency or percentages?
Yeah, so the key, in the book it says frequency or percentage can be listed. You can say either one, that's fine.
Good kitty.
Okay, so as I mentioned as I was gesturing at another question, one type of bar graph in which the bars are touching is called a histogram. You should do this if the variable in question is continuous.
On the x-axis.
On the x-axis, meaning ratio or interval. So if this is age, height, IQ, those are all continuous. And if you're not sure what's continuous, think, can you have a decimal, right? If you can have a decimal, then make it a histogram. Now, I drew it like this on purpose. So there's something called the normal distribution, which I'm sure we've talked about at some point. It's ubiquitous in the sciences. So strictly speaking, the normal distribution is a mathematical function. It's a curve. So there's an equation for the normal distribution, and the inputs you put into the equation are the mean and the standard deviation, and you get this function. And it is often a very good approximation for the actual data. So you can run a curve through the data, and it won't be perfect, but it is often a good approximation of where the data points are.
All right.
So if you want to, so technically, if we're going to do the definition accurately, you would write the equation, which of course I will not require. One sentence definition that's good enough for a class like this: it is a curve in which most scores are close to the mean. That would be one way of saying it that's good enough for a class like this.
So, like a frequency distribution.
So it's a curve that is a good approximation of a frequency distribution, but if you want to connect it to frequency distribution in the definition, that's
Did you say a curve in which all units are close to the mean?
not all, most. So, as you get further out, scores get rarer and rarer, right? The way it plays itself out, so like classic example is IQ. You've probably seen the distribution of IQ in intro, right? Around 68% of scores are between one standard deviation above and below the mean. That's a standard case of a normal distribution, right? Most scores are close to the mean, but they get increasingly rare the further out you go. This is a bit out of order, but I'll do it this way anyways. Frequency polygon. So this is a histogram. You can represent the same data, but do it like this. And then, so this is different actually because I had one that's low, but that would be a polygon. So you have dots, points, and straight lines between them. So you're representing the same information, in this case, except there's one low one, but just with a different type of graph. So that's a polygon.
As dots?
Yep.
The book says that that's only used for continuous.
Yeah, so both of these are only used for continuous.
Okay.
Yeah. Both histogram and polygon. Okay, so now we'll talk about some they're called descriptive statistics. Are there any questions on this before we move on? So the big distinction in statistics that you have to know is descriptive versus inferential. We've talked about this already. So descriptive statistics, those are used to describe or summarize your data. You know, you get your sample, you measure some things, and you describe what you found. So the mean, standard deviation, correlation coefficient, all of those are descriptive statistics. At that point, I point out that no one cares about your sample. That's the kind of hard truth. The 50 people you got, no one cares about. Inferential statistics are about drawing an inference from the sample to the population. But first we'll do descriptive. So one important type of descriptive statistic is central tendency. This is kind of a family of statistics. So central tendency numbers are numbers that aim to capture where the scores tend to be. So you look at some distribution. Okay, there's people all in here. Well, where do the scores tend to be? And you want to say something around here, presumably. But there are different numbers that capture central tendency, and none of them are perfect. They each have their sort of weaknesses. There are three main ones. This should be reviewed from Intro Psych. The three measures of central tendency are the mean, or the average, same thing, the median, and the mode. So the mean is by far the most commonly used. It's very simple. You add the scores up, divide it by the number of scores. So you learned that back in grade 8 or whatever. So unless there's something weird, that's the one you should default to. As I already mentioned, the key weakness of the mean is that it is sensitive to extreme values or outliers. If you were in my intro class, you'll have already heard me give this example, but let's suppose you're working for an aid organization and you're trying to find which village needs the most help. You're in some impoverished country, and let's say you find a small village with 4 dudes. And this is the wealth of the 4 dudes. 3 of them have $0, no monies, and then 1 dude has $1 million. So you measure everyone's wealth, and you report back to the aid organization, well, this village is doing great. The mean wealth of this village is, can anyone tell me? You should be able to do it in your head. To $250,000. So it's pretty good. So you add up, some people gave different answers. You add up the 4, divide it by the number of scores. So 1 million plus 0 plus 0 plus 0 is 1 million. Divided by 4, $250,000. So, which is pretty good. That's better than the median wealth here. But you wouldn't be lying, but it's misleading to say this village is doing great because the mean is high. The mean is high, but it's misleading. And there's a standard case where there's one outlier who's dragging the mean up. And that's a general weakness of the mean. It's sensitive to extreme values or outliers. So if there are outliers, often you instead use the median. The median is the middle score. You rank the scores from smallest to biggest, pick the one in the middle. If there are an even number of scores, pick the middle 2 and the one in between those 2. If there's an odd number, you literally pick the middle one. So let's say there's a different village, there's 4 dudes, let's say 5 dudes for the first one. One dude has $1, one has 2, one has 17, one has 100, and one has 121. Okay, 17 is the median. You rank them from lowest to highest, that's the median. If there's 6 people, so let's say there's another dude who has 18, then it would be 17.5, the one in between the 2 medians. Any questions on the median? Yes?
Sorry, I just have a question. So in the exam, are we just supposed to write the middle score?
Yeah, maybe the middle score after you rank them from lowest to highest. Yeah.
But if I like that from the numbers and then I just circle like the one that told you counted.
Sure. Okay, the last one is the mode. This can be useful to know in a few cases. Yep.
Just curious, what would the median be in the first example? Would it
0.
be 0?
Yeah. So,
You're supposed to use the median when there's outliers, but oh, okay, I see, because you're representing the zeros more than the nil.
yeah, exactly. It's more honest, right? If you go to the aid organization, like, you should have the intuition, this place needs help. And you're more honestly communicating that if you use the median. Now, in this case, actually, the mode would be 0, too. The mode is the most commonly occurring score. So if it's shaped like this, it's whatever score is here at the pointiest, the top part of the point of the curve. So that can be useful in like sometimes you just may want to know. So here, let's make it more skewed. Let's say it looks like this. There's a lot of kind of outliers over here. The mean will probably be here. The median might be here, and then the mode will be here. And it is interesting to know that that's whatever score is here. That's the peak. Another case where it's important to say the mode, or in this case modes plural, is in a case like this. This is a case of what's called a bimodal distribution. Bi meaning 2. So the median and mean in this case will both be about there, but that's sort of leaving out the most obvious thing about the distribution, which is there's 2 clumps of people. So some classes look like this. So when I took symbolic logic at Douglas, this is the I don't know why the prof told us this, but he's like, just so you know, this is what the grades look like. So basically, you either totally got it or totally didn't. Was kind of the 2 clumps of people. So far, this class is not like that. Hopefully, the next test is not like that. But that's another case where the mode or modes is worth knowing. Okay, that's central tendency. Any last questions? Okay, the other important thing to know is variability. So variability is like central tendency. It's an umbrella that includes different measures or different ways of getting at it. So actually, here's a story. So one time I was teaching AP Psych. So for years before I started teaching at the university level, I taught private AP psychology courses. AP Psych is basically intro psych, but for high school students. And I was seemed to break it down for them. So I was trying to introduce the concept of variability. And I said, like, imagine there's 2 classes, and both of them have the average score 70. But in one class, it's, let's say small class, it's 68, 69, 70, 71, 72. In the other class, it's 50, 60, 80, and 90. So they have the same central tendency, the same mean, and the same median for that matter, but they're different. Now put into your own words, what's different between these 2 classes? And one student confidently put up his hand, they meet in different classrooms. And I was like, he's not wrong, but it's not what I was going for. There's different amounts of variability, right? The first class or the top class, there's more spread between the scores. And there are real cases where these come apart. One finding in many studies, the mean IQ for males and females is the same, but many studies find that the variability is larger for males. Basically, more geniuses, more idiots. So important to keep these two apart.
All right,
There-
what's your one sentence?
How spread out the scores are. So there are three measures of central tendency that you should know.
We already went.
The first and the simplest, although it's rarely used, is the range. So the range is the biggest score minus the smallest score. So let's say, God forbid, in this class, the final grades end up being such that the highest grade is 100 and the lowest grade is 1. The range is 99. Very simple. Crucially though, the problem with that is you're missing out on a lot of information. You don't know how spread out the other scores are. You just know the highest and the lowest. So the two that are more commonly used are standard deviation and variance. So here's what I'm going to do. I'm going to give you a definition for each that's good enough for the test, but then I'll show you how to calculate it. Just so you know, and I'll do it in kind of an intuitive way so that you can have it in your head. But here's the definition that's good enough for the test if you want that, one sentence definition.
Yes.
Not looking at anyone in particular.
That's what
so-
you asked for on your test.
No, yes, I know.
You're talking about this like I'm being unreasonable.
No, I didn't say it was unreasonable. For standard deviation, how far away, on average, are scores from the mean? I should say, that's not strictly speaking right, but it's a good first approximation. And it's a good enough first approximation, as I say, for the test. So if you think about, the classic case, is IQ, so the average IQ is 100, the standard deviation is 15. What that means is, okay, some scores are very far from 100, some are very close. 15 is how far away on average IQ scores are from the mean. So that's a good enough one sentence definition. The variance is the standard deviation squared. That is literally true. So that's not a first approximation, that's just literally true. Yep.
Just wondering if we memorize an answer from 2300.
Yes. Yeah, if you write the
Gave you the long answer?
if you give me a long and true answer, that's fine, but I guess it's just riskier.
And so you're literally just the standard deviation squared is an excellent answer for a test for variance.
For variance, that's fine. Yep.
Okay.
It is what it is. So, if that's good enough for you, you can just turn your brain off for the next 3 minutes. I'm going to open up a Google Sheets file and show you how to calculate standard deviation. This is good to know for. No, I will do it.
Google thought it could teach the class better than you.
Oh wow. But one day, I'm sure one day there will be an AI that's better at teaching it. Okay.
I think nobody said hey, you were.
So, let's say this is a range of grades. So, let's say this is a class. So down here we have the mean. This is the mean grade in this class. Yep.
Make it bigger.
Yes.
Thank you.
Okay. So, this is the mean. So here's the first thing you do. You want to get the deviations. The deviations are how far away each person is from the mean. So take each person, subtract the mean. So just start with this one. I did this minus the mean. That should look right. Right? That person is 17.1 points below the mean. Right? So take each one and do that. This is how far away each person is from the mean. Okay, so now the first instinct you might have is, well, why don't we just average those together? Well, let's try adding them first. So equals sum, so that means add together all these. 0. And when you think about it, that has to be true, right? They cancel out because on average, scores are the mean, right? That's what the mean is. So what we want to do is make these values all positive. There's different ways of doing that. The way that we do it if we're calculating the standard deviation is we square them. So we take each score and multiply it by itself. When you multiply a negative by a negative, you get a positive. And when you multiply a positive by a positive, you obviously also get a positive. So we take each one, raise it to the power of 2, which is the same as squaring it. And then we'll just do that for all of these. So now we have all of, these are the squared deviations. So it's how far away each score is from the mean, squared. Each of those numbers you square it. Okay, so then we get the average of all those. And that is the variance. So another definition of the variance you could write is it's the average squared variance. But now this number should look kind of silly, right? Because you look at the deviation, so how far away scores are from the mean, none of them are anywhere near 100 points from the mean. So this is 100.2 something, so that should look kind of silly. So, but remember, when you square something, yes, you're making them all positive, but you're also making them bigger. So you cut it back down to size, we square root the variance, which I think is SQRT in Google Sheets. Square root the variance, ta-da, that's the standard deviation. And that should look right. You look at the scores, yeah, like one of them's 9, one of them's 1, one of them's 8, you know. How far away are they on average from the mean? Around 10. So that, very quickly, is how you calculate the standard deviation. As I say, you don't have to do that on the test, but for some of you, for your future classes, that may be helpful. Yep.
Is the variance something that a researcher would report, or is it just a means to get to the standard deviation?
Usually it is a means to get to the standard deviation. It is reported, it's used in some kinds of statistics, but it's less helpful in terms of understanding your data set. The standard deviation is much more helpful. Okay, that's the end of variability. So the next section is on different kinds of comparisons you can make. So one comparison you can make is you can compare group percentages. So let's say you might be doing a comparison of cognitive behavioral therapy to nothing. So you randomly assign people to conditions. And you might be asking, what percentage of people get better? And you have some definition of get better. Like maybe get better means you go down by more than 4 points in the Hamilton depression scale, or inventory, I forget which. But you go down a certain number of points in the HAM-D, we'll call that as you got better. And let's say 65% of people get better with CBT and 30% get better with nothing. Okay, you have a big difference in group percentage. Or there was that funny field experiment I mentioned where you look at how many men versus women say yes to dinner versus say yes to bed. I think it was you who said, it's really unethical because of all those men who were disappointed.
That was me, yeah.
Okay. So that's another case where you're looking at group percentages. Comparing group means, pretty self-explanatory. The value in each one you're comparing is the mean. So maybe in this case, the mean Hamilton depression score in each group. Right? We can compare those.
So it's literally just comparing the means from two or more groups,
Yep, exactly.
and so comparing the percentages from two or more groups?
Yep.
Okay,
Yep, those two are pretty straightforward. Actually, I shouldn't have erased that. Well, a similar concept, effect size, which hopefully you all reported in your paper. Effect size is about how big the difference is between two or more groups. You can also have effect size measures for correlations, but we'll focus on the cases where it's comparing two or more groups. And if you write a definition that relates to that, that's fine. So again, it's how big is the difference? A very common measure of effect size, again, it's the one that you should have had in your paper, is Cohen's d. So Cohen's d is how many standard deviations apart are the two means. So, you have two distributions. Each distribution has a standard deviation, but you'll get the pooled standard deviation and use that. Well, actually, here, I'll just write down, here's the equation for whatever it's worth. It's mean 1 minus mean 2 over pooled standard deviation. Pooled standard deviation basically meaning the average standard deviation for both groups. If they have the same standard deviation, that's really simple. So let's use a more intuitive example. Let's say you have, I think I used this in an earlier lecture, but you have an IQ pill. You have a pill that you hope boosts IQ. So standard deviation for IQ is 15. So your control group has a standard deviation of 100. The experimental group has a standard deviation of 115. And let's just say they have the same standard deviation, so both groups have a standard deviation of 15. Cohen's d in this case would be 1. Right? There's one standard deviation between the two groups, between the means of the two groups. That would be a large effect.
yeah.
So this is just by convention.
Just say mystic.
So this is what different standard deviations would look like. So we're assuming here normal distributions for both groups. Cohen's d of 0.2, so only 1/5 of a standard deviation between the groups. So there it's mostly overlap, right? You can tell that the two distributions are separated to some degree, but it's mostly overlap. By convention, 0.2 is called a small effect. By convention, 0.5, so half a standard deviation between the groups, is called a medium effect. And by convention, 0.8 and up is called a large effect. So you can see there, the groups are really starting to be more different. By the way, that is about the effect size you get for different types of therapy. So therapy versus nothing, you get something like that. And just to answer a question that I had when I first saw this, yes, you can have Cohen's d's larger than 1. In theory, you could have Cohen's d of 100. I mean, you would never see that in psychology, but it's just how many standard deviations apart the two groups are. So, in theory, it could be as many as you want. Okay, correlation coefficient we've already seen before. So that's, it describes how strongly two variables are correlated. So of course, they range from -1 to 1, 0 means no correlation, so this. Correlation of positive 1 would mean they are perfectly linearly correlated. And then minus 1, they are perfectly linearly negatively related to each other. And basically the more tightly clustered around the line they are, the further away from 0 the correlation coefficient will be. So something like this, where so here they're all on the line. If they're sort of like this, so pretty tightly clustered, maybe 0.8 or 0.9. Yeah, pretty strong correlation. And then all of these graphical representations are scatter plots. Scatter plots are just a graph that represents a correlation. We already mentioned outliers earlier. And for the purpose of studying, I would focus on examples of outliers in relation to the mean, but outliers can also come up in outliers can come up in correlations too. So here's a real example. So I think I mentioned in a prior class Richard Wilkinson's work on the relationship between inequality and various societal outcomes. One thing that critics point to that often is an issue is on a lot of these scatter plots, the US is an outlier. So what Wilkinson would do in this is he would have graphs where you have inequality on the x-axis, like income inequality, and different countries have different amounts of inequality, and then some bad thing here, maybe crime, for example. And you limit yourself to like developed countries. And what you often find is there's maybe a sort of correlation here, and then there's like the US, which within the developed world is often like the most, if not one of the most unequal societies and highest crime rates. And with that, you can get a strong correlation. And then if you remove the US, which you maybe should, maybe the correlation's not so clear. So again, representing on a scatter plot can help you notice things like this. So that's something to be aware of. It's not quite that extreme, but the US is often an outlier. Another thing to look for or to be aware of when you're looking at correlations is restriction of range. Restriction of range means you are looking at a narrow range of people. Or you could say
possible people.
Of all the possible, or of all relevant people.
Yeah, relevant, possible.
Yeah. In a way, it's an example where you have an unrepresentative sample. That's a related issue. So here's one possible case. The relationship between GRE scores and grades in grad school. So if you look just within people who go to who actually go to grad school, the correlation's not super high. It's maybe 0.3, something like that. But what some people often point out is there could be a kind of, well, there is a restriction of range because the kinds of people who wind up in grad school tend to be people who have at least somewhat high GRE scores. It might be that like if you just let everybody into grad school, it might be that the relationship would look something like this, where it's initially positive, but then relatively flat. Sort of above a certain point, the correlation's not that strong. And by the way, that is often true. So like if you look at, you know, higher IQ, higher GRE scores sort of have diminishing returns. Once you're past a certain point, it doesn't make that much of a difference. Just as one concrete example, where I won't give names, but two people I was very close with in my master's program, This is when I did my master's in philosophy. And in philosophy programs, the way you bond with people is by arguing about things that don't matter. So that the three of us would like argue politics and philosophy and stuff. And you know, we don't know, what's your GRE score? We would talk about things like this. So one of them had a perfect GRE verbal score, which is very unusual. This is tests that are only taken by people applying to PhD and master's programs. And when we would have debates, you could tell he was a bit sharper, right? He was a bit quicker on his feet, had a greater command of facts. The other guy still did reasonably well, but he wasn't this kind of like uber genius kind of guy. But the other student who did like decent but not amazing on the GRE was a much better graduate student. And the reason is he worked his ass off. He had, by the end of his master's, I think 3 or 4 first author publications, which is very good even for like a PhD program. And this is just at the end of the master's. And the 3 of us traded master's theses, and you could tell the other guy who had like perfect GRE verbal, he basically just wrote it like in a week because he was used to being able to do that. But the other guy, like every sentence you could tell he had been over multiple times. So past a certain point, you know, doesn't matter that much. You know, it's other variables that make the difference. Now, if we, back to the issue of restriction of range, if you look at the correlation between GRE scores and performance, by definition, you're only looking at these people, like the people who got in. And if that's the case, if you're only looking at people who got in, that's an example of restriction of range. If that doesn't help, here's another example. In this case, it's more well established that there's a restriction of range issue. The relationship between income and happiness. Some of you may know, after a certain point, and it depends on what study, but maybe something like $75,000 a year, give or take, income stops making much of a difference to happiness. The correlation kind of flatlines. So restriction of range might be, you know, let's say you do a study, but you only look at upper income people, and you find, there's no correlation with between income and happiness. That's true within that limited range, but if you widen the range, you would see that at the lower end, there is a correlation between income and happiness. Does that make sense? I went on a bit for this one, so hopefully that one's clear. Okay, the next term, this is a really useful one to know. It's just a good one to have in your head when you're reading and seeing correlation numbers. I'm in the habit of, I kind of do this in my head automatically, because the number you get is really easy to interpret. And that's the squared correlation coefficient, or R squared. So R is the number for the correlation coefficient. So the correlation between 2 variables. So here's one real world one. The correlation between, so it's similar to what I just said, IQ and grades, say in high school, is about 0.5. Actually, rather than draw it, I actually have, for my intro class, real data. I think actually this might come up and answer someone's question. But a correlation of 0.5 looks something like this. So this is real data. So in that case, R equals 0.5. But whenever you see an R, you should square it in your head. What R squared tells you, so whenever you square a decimal, the number gets smaller. So 0.5 times 0.5 is 0.25. This smaller number is what percentage, or what proportion, of the variance in one of the variables is explained by its relationship with the other variable. So I know that was a long definition, I'll give that again. So what proportion of the variance in one variable is explained by its relationship with the other variable. So to make it concrete, in this case, what we're trying to explain is variation in grades. That's what we're interested in. And we're explaining it in terms of its correlation with IQ scores. So there's a certain amount of variability in grades, right? Just look at the scatter plot. There's lots of variability in what grades people get. What this means is 25% of the variability in grades is explainable in terms of its relationship with IQ, or you could say is due to IQ. Now, due to is a little misleading. This is strictly speaking a correlation, but it's a kind of upper limit on how much IQ explains in the variation in grades. And that should help you relax a little bit about correlations, right? So, you know, in this case, the relationship between IQ and grades, right, it's clearly positive, but another way of saying this is 75% of the variation in grades is things other than IQ. So, which is sort of good news, I suppose. So that's the squared correlation coefficient. Does that make sense? Yep.
Just have a question about the word explained. I know that's like a common word, but it's a little confusing in this sense. Does it mean just that if GPA goes up by 5 points, it's probably because the person has a higher IQ or something like that?
Good. So explained here, it's a little it's the one that's used in textbooks, but it's a little misleading because it might hint at a causal relationship, which it's purely correlational. So it means if you want to account for the variation in one variable, you can say, okay, this much of it is, yeah, so I'm trying to think of a word that isn't synonymous. Here's what I'll say. On the test, you can write explain, that's like standard, but it's explained in a correlational sense.
So if one thing goes up, you'd expect the other thing to go up.
Yes, that's fine.
It's just like, it happens to go up.
Yeah.
One goes up, it's just, the other one should go up by that amount.
Yes.
But
Or-
I don't know why, though.
Yeah, exactly. You're not exactly sure why. So the term explained, you're right to complain that it might be misleading, but it is the one that's used in statistics. I saw another, yep.
Heritability, is that also similar to R squared? Because my understanding was it's like also the percentage of a trait
Yes.
is caused by genetics. That would be similar to R squared, not.
Exactly, yes. Heritability is similar to R squared. Now, one thing I will say about heritability, though, and some people might disagree with this, but there I think you are justified in making a causal inference because the numbers that you get come from sort of natural experiments. For example, like twinning is a kind of natural experiment, right? Whether the twin happens to be identical or not is a kind of random assignment procedure, right? It's one that's done by nature, and so some twins happen to get double the genes in common. And so I think you are safe in saying, okay, this much of the variability is caused by genetic differences.
I just add, in a certain population, because we've seen
Yes.
heritability change from country to country. So,
Yes, exactly. So yes, within a certain, that's one thing I always point out. There's lots of caveats you always have to add with heritability because it's easy to misunderstand. And yes, it's, within any group at any given point in time. Whenever people hear genes or heritability, their brains go straight to group differences, which is exactly not what it's about.
Yeah.
But yes, so you're right to add that caveat too. Okay, so the next one, regression equation. This is the equation for the line that goes through the data points in the scatter plot. So let's say you're looking at the correlation between psychopathy, as measured by, let's say, the psychopathy checklist revised, and criminal offenses once you leave prison. So you sample a bunch of criminals, and you find that there's a positive correlation. The line that is the best fit for the data, that's the regression equation. So there's actually, here, I'll make this. Now, why would we do this? So a regression equation is really useful because it helps us to make predictions when we don't have when we don't know what someone's going to do. So in this case, we know how many crimes each person committed, and we know their psychopathy score. So we run this line through the data. But now we get a new guy, and we don't know how many crimes he's going to commit. We're deciding whether to let him out of jail or not, or out of prison. But we know his psychopathy score is here. Well, the best guess for how many crimes he's going to commit is here, right? That point on the line. So if we don't know for sure, this can be really useful for informing decisions like that. So in this case, maybe keep the guy in prison for longer. He is more likely to commit crimes once he gets let out than Jim over here, who has a psychopathy score here. Now, of course, there will be exceptions, but if we have limited resources, this can be useful. Yep.
I noticed that when you draw a lot of the lines start at 0, 0. Is that true, or is it?
Start at what?
At like the point of 0, 0-ish?
Oh, no, so they don't have to. So that's what I was
They
going
start
to.
wherever. Okay.
Exactly. So wherever the best fit is. So actually, the equation has the following form: y, and y is this one. Now, which one goes here and here is a matter of choice. The one you put here, two things. One, it's the one that you're trying to predict. In this case, you're trying to predict crime. And two, it's the one that you want your readers to subtly assume is the one that's caused by the other one. You can't come out and say it because you know it's a correlation, but you're kind of like, this one's the effect, right? We can agree. So that's the y1, which will go here, equals a plus bx. A is here. It's the y-intercept. So it's the point at which the line hits the y-axis. The regression line hits the y-axis. X is this variable, so psychopathy score, and b is the slope of the line. So rise over run from high school math. I know you all repressed that, and you don't have to know it for the test, but just for whatever it's worth, the slope is what goes here. So then so then you get a new guy into the lab, you get his psychopathy score, crunch, 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 calculate, and you find out what his predicted y is. So what you would, how many crimes you predict he's going to commit based on this regression. Okay, related terms, y, so crime in this case, is the criterion variable, which is just the variable you're trying to predict. And then predictor variable is the one you're using to inform your prediction about the other variable. So in this case, psychopathy score.
That really, you said that was the x-axis?
Yes.
Yeah.
Yeah, the predictor variable by convention goes on the x-axis. The criterion variable by convention goes on the y-axis. I forget if I mentioned this, but Brian Nadeau, who sadly passed away this semester, used to do this. He used to interview sex offenders and other criminals and see how psychopathic they were in order to inform whether they would get let out or not. Cool stuff. Okay, well, first of all, any questions about this? Yep.
Just a clarification that this is more of a simplification, right? Because isn't the regression equation trying to predict how much of the variability in y is due to x?
So this equation, no. So this equation is for the line. So the regression equation is the equation for the line. Now, there's another number you can get that relates to how much of the variation in one is due to the other, but the regression equation is you get a specific prediction. We predict based on this that someone who has a psychopathy score here will be here. And then there's other terms that relate to how much of the variation is this one.
Okay.
Okay, so that's this case. Now, the book lists the terms multiple correlation and squared multiple correlation coefficient. Those shouldn't be on the key terms. I've crossed those out, so don't worry about those. We will worry about multiple regression. So multiple regression, you don't have to visualize this one. And in fact, if you have more than 2 predictors, it's not really possible to visualize it. So I'll just explain it intuitively. So let's stick with the crime case. So we have Jim in front of us, and we want to predict whether he's going to commit crimes once we let him out. But we want to take more into account than just his level of psychopathy. Let's say that testosterone levels are also, which they are also correlated with his likelihood of committing a crime. And this will be a big one. How many offenses he committed before going to prison? So now we have 3 predictors. We have psychopathy, testosterone levels, and number of prior offenses. And we can put all of those into an equation to give us probably a more accurate prediction about how likely he is to commit a crime once he gets out. So that would be an example of multiple regression.
And your 1-sentence definition.
Using multiple predictor variables to predict a criterion variable. And you can define it on the test without using those fancy terms if you want. You could say, for example, using these 3 things to predict this other thing, that's fine too, if you'd rather do it that way. Okay, so with multiple regression, you're putting all of these things in to predict the same thing. The next one, partial correlation, it may sound at first glance like it's similar, but it's very different. So let me start with an example before I give a definition. So think again of the example of IQ being correlated with grades. So, and now the arrow here is misleading. Let's put it this way. Let's say your hypothesis is that higher intelligence, as measured by IQ, leads to higher grades. That's what you think is going on. But it's a correlation, so you can't really know that. One of the possibilities is that there's a third variable that affects both. So here's one example. So, and this probably is part of what's going on. There's socioeconomic status, right? Basically how rich and high status are your parents, right? So socioeconomic status is correlated with higher IQ, right? You get better nutrition when you're a kid, more books in the house, whatever. All of these things could potentially raise IQ. And it might also affect grades, right? Your parents can afford the fancy tutors, and there's less stress in the home, you have more time to study. All that stuff may lead to better grades. So all 3 of these are going to be positively correlated, probably. So here's what a partial correlation would be in this context. It's the correlation between IQ and grades while controlling for socioeconomic status. You don't have to do this. I don't remember. But just understand conceptually, that's how it works. You're looking for the correlation between, so if you want a definition that's just abstract, a correlation between X and Y, if you like, while controlling for a third variable. And here's the upshot of this. Let's say that there's still a correlation between IQ and grades, even when you control for socioeconomic status. We have not thereby established causation, but it's like a little nudge. Okay, we're at least a little closer to that. We've at least ruled out one, or provided evidence against one possible third variable explanation.
But could you still say that if the correlation value went down?
So if the correlation variable goes down, which it probably would, at the very least it shows the extent to which this causes this is the kind of upper limit of how much this causes this is lower. That leftover correlation could still be causal. We don't know that for sure, but this is like nudge, nudge, maybe. We've ruled out one possible alternative explanation. And if you control for a bunch of third variables, your confidence that it's causal goes up, though never as high as it does if you do an experiment. Which you can't really do. You can't really randomly assign people to different IQ levels.
Or being bored out.
Or it would be unethical. We're just gonna hit you in the frontal lobes and decrease your IQ. And your grades went down. You can now make a causal inference.
Isn't there always another third variable that you don't know about?
No, exactly. That's why I say you can't establish it. So you can't control for every possible third variable. Yeah. So what you'll do, so this is what is actually done in real cases where you can't do an experiment. You try to control for sort of the obvious ones. So in this case, SES is an obvious one to control for. And maybe you control for a few others, and you say, okay, one reasonable interpretation is that this relationship is causal, but of course we don't know that for sure. The next term, which I think is in the key terms, but I'll tell you right now it's not on the test, but I'll just gesture at it so you're aware that it exists. This one, it's not that I forgot how to do this, I was never taught.
No.
I would have been taught if so here's one fun, this is just something that's true about life. It's very arbitrary. Little changes make a big difference. Like, so one example is, when I was applying for graduate school, I made a long list of programs, and then I would just rule out programs if none of the professors worked on one of my three areas. So my three main kind of interests were moral psychology, psych of religion, and cognitive bias. So if no one did at least one of those things, the school got the axe. So I was going through schools. I was at Georgia State at the time. Georgia State was on the list. They had a PhD program with people who did stuff like that. I got to the University of Alberta. I was this close to cutting the list. I got to one professor who had one publication listed on moral psych, so I decided to not cut it. It turns out that guy actually had done work on all three, but his uni page just had like a few papers. That wound up being the school I went to, the U of A. If that prof had not listed that one paper on his short bio, I would have done my PhD at Georgia State. So kind of a funny little thing. Georgia State required that you learn structural equation modeling. The U of A did not. As a result, I do not know how to do it, but you will see it in papers. Here's just an example I took from Google Scholar. Structural equation modeling is entirely correlational. You look at many variables and how they're correlated. You try to control for some of them. And what this allows you to do is to test hypotheses about causation. You have a hypothesis about which thing causes which, and you can do this to see which causal hypothesis is more consistent with the pattern in the correlations. That's all I can say. It will not be on the test, but you may see things like this, or some of you may go to graduate programs where you have to learn it. So, little teaser if you go to some PhD programs. So that's structural equation modeling. The book has a brief discussion of it, but I will say no more. Okay, next, we're back to our old friend null hypothesis significance testing. We've already seen this before.
Next is inferential statistics.
Yeah, so inferential statistics is an umbrella that includes NHST. So just to review, so you have your population, you have your sample. Inferential statistics are about making an inference from your sample to the population. Because as I said earlier, no one cares about your sample.
Would it be fair to say how well statistics generalize to a population?
I wouldn't say how well. I mean,
Or the process of?
the best way to say it is just numbers or statistics that relate to making an inference from the sample to the population. And actually, this is a pretty natural place for a break. So let's take a break. We'll come back at 4:55. Okay, so let's keep going with inferential statistics. This is review from earlier, but it'll be relevant to one of the written. So reminder, null hypothesis significance testing. This is by far the most commonly used procedure in inferential statistics, at least in psychology. So you have here null hypothesis, which is almost always the hypothesis that there is zero effect or zero correlation. From that, you derive, from that and your data, you get a p-value. The p-value is the probability of getting your results if the null hypothesis is true. Yeah, so the probability of getting your result if the null hypothesis is true.
And the null hypothesis is basically a reason that there's no association.
There's no association or no effect. So I'll just use, this is the example I used earlier, but you've probably forgotten it by now. So let's say we're looking for a difference in video game playing behavior between men and women. So this is the population. So the null hypothesis would be that the difference between men and women in hours of video games per week is 0. There is no difference. The mean number of hours per week is the same. So then you get your sample, 100 men and 100 women, and you get a mean difference. So let's say it looks like this. For women, it's 1 hour per week, and for men, it's 15 hours per week. So that's a very big difference, obviously. The p-value is what is the probability of getting that difference if in the population there's 0 difference. And as we said, the probability in a case like this would be very low, very small p-value, which is good. We want small p-values, maybe 0.0000. It depends on it depends on the standard deviation too, or on the variability. But small p-values are good, so null hypothesis significance testing works like this. You set a cutoff in advance, which we call alpha. Don't worry about that now, for this chapter. But you set a cutoff, and saying cutoff is fine. And we say, if the p-value is less than this cutoff, we will conclude the null hypothesis is false. We will say, no, there is an effect, or there is a correlation. So what's this? I hope you all know this one. What's the cutoff?
Of this 0.05.
0.05. So
You also have to set it.
But you have to set it. It's not just set to 0.01. Some people argue it should be lower, but this is by convention the cutoff 0.05. So we say if the p-value is less than this, then we reject the null or the ho, as I said.
Nice.
So the phrase for a finding with a p-value of less than 0.05 is statistically significant. Which, if you want to put it in layman's terms, it means it's sufficiently unlikely that we will conclude there is an effect. We will conclude that the effect is not 0. But here's an important distinction. There's an important distinction between statistically significant and practically significant. Practically significant means, does this result matter? Is it significant in more the layman's sense? Should I give a shit about this result? and these are not the same thing. And here's one simple reason why. One way that you can increase the chance that you'll get a statistically significant result is bigger samples. So the bigger the sample, the easier it is to get a p-value less than 0.05, even if it's a tiny effect. So here's an example. Let's say we get not 100 men and women, or 100 men and 100 women, but let's say 10 million each. 10 million men and 10 million women. And let's say the mean difference is one group plays 5.6 hours of video games per week on average, and the other is 5.8. With a sample that big, almost certainly the p-value is going to be less than 0.05. So this is going to be statistically significant. Because again, what are the chances we would get this with a sample that big if in the population the difference is literally 0? And it's actually pretty unlikely. When the sample's that big, these are going to be pretty close, probably, to the population values. So this is going to be statistically significant, but not practically significant. This result doesn't matter. In terms of predicting whether men and women play more video games, or what, it's a real difference. It's not 0, but who gives a shit is what you probably would say.
So is that like a real life example of some of the drawbacks of NHST testing?
Yes, this is an example of a drawback of NHST. Or a drawback, what it means is you shouldn't read too much significance into the phrase statistically significant. All it means is the result is unlikely to happen if the null is true. And so we're going to conclude there is a difference here. Even though in this case, it's a tiny difference. We're just saying the effect is not 0, but it might still be small. So that's a very important distinction. The distinction between statistically significant, which basically means we're going to conclude the effect is not 0, and practically significant, which means the result matters. It's important or significant in the everyday sense.
Sorry to yank you back, sir, but
No,
you
of course.
skipped effect size.
Good, so effect size does relate more directly to practical significance. So we talked about it earlier with Cohen's d. So effect size is, in the case of something like this, how big is the difference between the two groups? The reason I have it here, I was going to say this at the end anyways, the written question is about those 3 terms. Statistical significance, practical significance, and effect size. I'll say more about that.
Full beams.
So now I want to give a real world example. So this is one of the longer videos I show, but it's quite nice. It's a video of Robert Sapolsky. He doesn't use these terms, but it gets the point across. Okay, so as I say, a bit of a longer video, but really nice example. So if you're watching at home, Sapolsky is talking about this birth order effect. It turns out, I'm a firstborn, so I like this effect, that firstborns have higher IQs on average. And there's this long video of him discussing with students all the possible reasons for this. But the punchline, the difference is only 2.3 IQ points, which is not nothing, but it's pretty close to nothing. So even though it was a very big sample and you can be very confident that there is a difference there, it's not practically significant. Okay, another important statistic that can be added to NHST is confidence intervals. Again, this is reviewed from earlier. So the most common one that's used is 95% confidence interval, which again, you also should have included in your paper. So what that means is you're 95% confident that the population value is within a certain range. So, if the sample is big, let's say for the men, it might be plus or minus, 0.1 or something like that. But if it's a bigger sample, the confidence intervals will be smaller, right? Because you're more confident that it's in a certain range. And again, to no one in particular, if you want a one-sentence definition, you are 95% confident that the population value is in a certain range. So in this case, you're 95% confident that it's between 5.79 and 5.81.
Okay, so I'm so sorry to do this to you. Completely cutting out the 95%, or is that an important number?
Oh, so that's
for
one.
this?
So you can say just how confident, or you have a certain level of confidence that. Blah, blah, blah.
A certain level of confidence.
So usually it's 95 or 99.
Sure.
Which is good, right? So, because again, with null hypothesis significance testing, all you're saying is we are confident that the effect is more than 0. But with confidence intervals, you're asking, okay, how big is it? And more specifically, how confident are we that it's at least within this range? So in the paper, I had you report both the effect size and confidence intervals for the effect size. So we think the effect is this big, and we're pretty sure it's at least within this range. Now, given how small your samples were, probably most of you had quite wide confidence intervals. Okay, so the next section is on Bayesian statistics. I'll say two things about this. First of all, the terms related to Bayesian statistics will not be on the test. If it piques your interest, so some of you were asking about this during the break. So upcoming courses I'm teaching, I'll use this for some shameless self-promotion. So I don't teach in the fall, I have fall off, at least here. But in the winter I'm teaching 3309, which is basically a philosophy class. It's called Critical Issues in Psychology. The way I teach it, it focuses on philosophy of science and philosophy of mind in relation to psychology. So some people were asking because they wanted to join, so I'll just say for all of you, if you don't have the prereqs to join, but you've taken this class or even just you're interested in taking it, just send me an email and I'll waive the requirements. I'm 99% sure I can. So feel free to do that if you're interested in taking that. And the other one I'm teaching, it's provisionally dated for this next summer, is moral psychology. We still have to have a department vote to approve it because it's never been taught here before. Assuming it gets approved, I'll be teaching that in the summer.
The new one?
It's new, it's never been taught at Douglas. I did teach it at the U of A, but I've never taught it at Douglas. And it's already on my YouTube channel, but it's 305, because that's what it was at the U of A. For this one, the prereq is you have to take social psych, so try to take that before. But if you don't, and you really want to take it, again, just send me an email and I'll try to waive the requirements. But in 3309, I'll be talking about Bayes' theorem and Bayesian concepts in more detail, but I'll at least gesture at them here just so you have some sense of what's going on. Here's another weakness of NHST. It all centers around the p-value, and the p-value, as I already said, is the probability of data, or the probability of a result, which isn't really what we care about. What we really want to know is what's the probability of the hypothesis. That's what we want to know. How likely is it that this hypothesis is true or false? NHST technically doesn't give you that, but Bayes' theorem does. Bayes' theorem, when you crunch the numbers, gives you the probability of a hypothesis being true. The key extra ingredient you need, and again, in 3309 there is exactly one equation. It's not a mathematically heavy course, but I will actually explain and teach on Bayes' theorem, so it is an equation. In my opinion, it's a very beautiful equation. The key ingredient that is lacking in NHST is prior probability. This is not there in NHST. Prior probability is how likely is the hypothesis before you look at the new evidence? So just, in other words, just based on your background knowledge, the stuff you know before you do the study, how likely is the hypothesis? Now, this is somewhat subjective. You kind of have, in some cases, you basically just make it up. It's a bit more complicated than that, but you can use what's called an uninformative prior, where you try to have it exert as little influence on the calculation as possible. None of this you have to worry about, but basically, it's the probability of the hypothesis before you've looked at the new evidence. Just as a funny example of how this would be different in practice, albeit in a kind of silly example. Sorry?
A little bigger.
Yeah. So there's the frequentist and the Bayesian. Frequentist is basically NHST for our purposes. So did the sun just explode? It's night, so we're not sure. Oh, and it has the term bet. By the way, Bayesians are all about betting. It's all about how much you would bet that something is true and how confident you are in different hypotheses. So we have this neutrino detector. It detects neutrinos and then calculates whether the sun went into nova or not. But then it rolls 2 dice, and if they come up 2 6s, it lies to us. So it tells us the opposite of whatever it actually found. So let's try our sun detector. Did the sun go nova? Yes. The frequentist says the probability of this result happening by chance, which is a little bit of a sloppy way of putting it, basically the probability of this if the null is true, 1 over 36, 0.027, so it's less than 0.05, so I conclude the sun has exploded. But the Bayesian says, I will bet you that it has not. So the key missing ingredient is the prior probability. The prior probability that the sun has exploded 5 billion years early is very, very low. And therefore, we do not conclude the sun has exploded. So some of I'm very sympathetic to the Bayesian approach, which is coming through with this example. Having said that, NHST is still much more commonly used, so you should know how it works.
The book actually says that they're using p-values less.
Yeah, so many people, especially statisticians, argue p-values should be used less, or at least less importance should be placed on them. And as far as actual practice, they're losing. There is one social site journal that a few years ago banned p-values, and they said just do not tell us p-values. But that's a tiny minority. So I think a more winning strategy is to ask for more. Like, yes, give us the p-value, fine, but also tell us effect size and confidence intervals and things like that. Oh, and just one other example for Bayesianism being at least implicitly relied on. Think back to the Darrell Bem case, right, where Darrell Bem found evidence that he claimed was evidence of ESP. Well, again, your prior probability in ESP should be low. So that's another. Okay, that's the end of chapter 14. Any questions?
Posterior?
Okay, so posterior probability is the probability after you've added the new data.
And your 1-sentence definition for Bayesian statistics.
So it won't be on the test, but it's statistics that uses Bayes' theorem is fine. Even though, as I say, it won't be on the test.
Normal prior probability or posterior?
Exactly, neither of them will. One cute saying, though, that I'll say, that what Bayesians say is today's posterior is tomorrow's prior. Right? So once you've done the study, then the posterior probability you'll use as the prior the next time you do it. So that's kind of nice.
So Bayesian is the one that will be right?
No, all three won't.
All three?
So all three relate to Bayesian statistics. So those are just if you're curious. As I say, all of those will be going into more detail in 3309 if you wish to take it. Though, as I also said, that's the only equation in that class. Okay. The last chapter of the book, the catch-all term is generalizability. It's not a testable term, but it's the term you should have in the back of your head as you read it. So it's about the extent to which our studies will generalize to the real world, or will generalize to the population. And there are various ways that this chapter says we should improve our generalizability, different ways that we can get better. So the first one, the term beyond university students. So most psychology studies, by the way, including most of mine, so this applies to me as much as anybody, use psychology undergrads as their subjects. This is because psychologists are cheap and we don't have to pay psychology undergrads. So that's a big advantage. But the big disadvantage, of course, is most humans are not psychology undergrads. So if we want our results to be generalizable, moving beyond psych undergrads is a good idea. Relatedly, we should move beyond volunteers. So most studies use convenience samples. You'll recall from an earlier chapter, convenience sampling is the least sophisticated way of getting samples, and therefore we have the least confidence that the sample is representative. So we should use more sophisticated sampling methods when possible. Like random sampling, stratified sampling, etc. Beyond gender, we should aim for samples to be more representative vis-a-vis gender. Ironically, in the case of psychology, historically, many sciences had the opposite problem, but psychology samples usually skew female, if anything. The reason is most psychology undergraduates are female. Roughly 75% of psych BAs are earned by women, as it turns out. So that's a potential issue. The book also mentions having more diversity vis-a-vis people who have other sorts of gender identities. Some older studies would exclude people like that for convenience, but that is important for the sample being representative. By the way, philosophy is almost perfectly the opposite. So I've been both a psych and a philosophy major. Philosophy is about 75% male, so kind of a mirror image. Like, if you go to philosophy grad school, I would say a good solid half are just men with autism. And I'm allowed to say that. It's almost a prerequisite to get into philosophy is to be a man with autism. Maybe I'll edit that part out. But, okay. Next, beyond culture. How many of you have heard of the weird problem? So, very commonly used term now. Most samples in psychology come from weird countries. It stands for Western, educated, industrialized, rich democracies. So basically, Western Europe, Canada, United States, Australia, New Zealand, places like that.
Wait. What's the I?
Industrialized. So, again, most people on Earth are not from weird countries. This term was actually coined by a UBC prof, Joe Henrik, and I think the first paper was called something like "The Weirdest People on Earth." And what he meant was, not only are these people not representative, in many ways they are the most unusual compared to other cultures. There are various dimensions on which they are not only unrepresentative, but very unusual. And this affects things that you might not expect. So just one concrete example, there's a bias in social psych called the fundamental attribution error, which was called that in part because it was so well replicated. We thought this is just a core feature of human nature, this bias. Turns out either doesn't exist at all, or at least is much smaller in non-Western samples. Now, okay, a social psych bias, that's not that surprising that would vary by culture, but even things like visual perception can vary by culture. So you will have seen this if you were in my intro class. How many of you have seen this before? This is the Muller-Lyer illusion. So which line looks longer, the top or the bottom? And well, obviously the overall thing is longer, but the line in the middle, ignoring the triangle-y bits. Which one looks longer? Who thinks top looks longer? Who thinks bottom looks longer? Right. So overwhelming majority think top. This is culturally variable. There are some cultures in which you don't find this bias. Now you might think, how in the world could that be the case? And here's why. There are no right angles in nature. If you grow up in a more traditional or maybe hunter-gatherer type society, you're not going to be used to seeing things like this. When your visual system develops in response to things like this, you get used to making the following correction. You look at this and think, okay, this line is farther away, given that it has that shape, and therefore we're going to assume this is longer than it appears. The image on my retina is smaller, but this line is in fact longer. And so your brain develops the habit of making that correction, and then in a case like this, the habit misleads you. But if you don't grow up surrounded by right angles, you don't develop that habit.
So which one is longer?
They're the same.
They're the
Yeah,
same.
they're both the same, right?
Yes, they're exactly the same. Yeah. And if you don't believe me, you can Google the image and put it in Microsoft Paint or something. Just confirm for yourself. Okay. Next, beyond the experimenter. So this is just a fancy way of saying we want to control for experimenter expectancy effects or experimenter bias. So it's important that there be not just replications, but replications done by other researchers. In the ideal case, researchers who don't agree with your theory. Right? That's you know, to me at least, when I read the literature, if I find someone who reports an effect that they weren't expecting or that their prior work argued against, I take that very seriously. Right? That shows that even though they weren't necessarily biased in this direction, they found this effect. This can have, even effects in animal studies. Paul Meehl, who has great lectures available online, by the way, at least if you're a nerd. So he had done animal studies, and he's reported anecdotally that the kinds of people who deal with the animals, it makes a difference what patterns you get. How nice the experimenters are to the animals. Now that kind of thing's not getting reported in the methods section. Like, oh, the nice graduate student handled the rats. But it matters, and therefore it's important to make sure it's replicated with multiple experimenters. Okay, beyond the laboratory, basically a fancy way of saying we should also do field experiments. So not just experiments in the lab, but experiments in the real world. So one, technically this is a quasi-experiment, but I mentioned it earlier as an excuse to make a joke, but one where they go into the university and ask random people for dates or sex, like that's a kind of field experiment where you don't have to worry about certain biases that exist in the lab because people know they're being measured and they therefore behave differently. Okay, any questions on the beyond terms? Yep.
For weird, you said they're not representative of the population?
Yeah, exactly. Especially because, look, we present psychology as this is the science of the human mind and human behavior. But if we're only looking at weird countries, it's not really the science of human thinking and behavior. Or if you say it is, well, you have a very unrepresentative sample.
So for a Veblen test, we just have to say that it's just.
Oh, so for weird, does it, in the key terms to say weird problem? Yeah, so it's just the fact, you could just say the fact that most psychology samples come from. You can even just say Western for shorthand countries, that's fine.
Okay, so just, that's all, it was just.
Yeah, that's fine. And if you want to add, and therefore the sample is not representative, yeah, that's fine. Okay, so next we return to the replication crisis, and I should say just issues in general related to replication. And I'm going to end this section with some good news. I front load you with bad news vis-a-vis the replication crisis. So stay tuned for the good news. But first of all, there's a distinction the book makes between direct replications and conceptual replications. This is more of a continuum than a clean distinction. But a direct replication is where you replicate the study exactly, or as exactly as possible. So let's say you're a psychologist in the old days when it was just getting started, and you want to replicate Pavlov's dog stuff. If you're doing an exact replicate or direct replication, you do the thing with the dogs and the bell and the food, right? And try to set it up just like Pavlov did, and see if you get the same pattern. So that has its virtues. You're making sure that the effect in question there is a real one. But a conceptual replication is where you try to replicate the general pattern, but with somewhat different conditions. So maybe you want to replicate classical conditioning, but not exactly with a bell and a food, maybe with, a snap noise and an electric shock. So, and in fact, you do find the same thing. So, snap, shock the dog, snap, shock the dog, and eventually you get the same aversive kind of flinching reaction just from the snap. So you've replicated the general pattern, namely classical conditioning, but with somewhat different variables.
Did you say you're replicating the hypothesis?
Yeah, replicating the hypothesis, but with different operationalizations, or different operational definitions. And the idea there would be, look, doing direct replications are very important, even though you don't get a lot of cred in the scientific community for doing direct replications. Many people have argued, I would say rightly, that we should do more direct replications, but people are less impressed because it doesn't require much creativity, you just do the same thing. The idea with conceptual replication is we don't want these patterns to only exist in narrow cases. We want them to be more, more general patterns. Okay. Does that distinction make sense? Any questions on the two types of replication? Okay. Next term. So this is widely thought to be the gold standard in the field, which is a meta-analysis. So meta-analysis is where you take all studies you can find in a given area and average them together. So let's say, it's kind of an interesting fact. Men and women have the same average IQ, 100, but there are differences in some of the sub-tests. So for example, women on average do somewhat better on verbal fluency tests. Men do slightly better on things like spatial mental rotation. And suppose you want to know, okay, how big is the difference? Some studies find no difference, some find a medium difference, some find a small difference. Okay, smash all the studies together and get an estimate of how big the effect is on average between the different studies. So this is, as I say, widely considered to be the gold standard, but those old issues with p-hacking and other kind of questionable research practices as they relate to the replication crisis, they do rear their ugly head here. There's a term you'll hear when people critique meta-analyses, which is garbage in, garbage out. I mean, you hear this in many contexts. So, in other words, if all the studies you put into the meta-analysis are p-hacked or the result of publication bias, you can't really trust the result you get from the meta-analysis. One way of correcting for that is you can try to include unpublished studies. So there are some manuscripts out there that you can find in various ways that were not published, but the data sets are available through various means. So you try to include those in the meta-analysis. And then there are some more fancy statistical things you can do to try to control for p-hacking and control for publication bias, but those have their own deficits. And to talk a bit about these issues, I'm going to show another section from the podcast, Two Psychologists, Four Beers. Yep, go ahead.
I've seen some people discussing the analyses that look like they have really good results, but when they actually do the statistics on their end, they find terrible or negligible results for individual studies. Is this kind of what you mean by, like, they're sort of fabricating an effect by picking certain things?
That's not, so that can happen. That's not what I'm referring to is the meta-analysis, the people doing the meta-analysis might have done it in a totally valid way. Now, there are decisions you have to make when doing the meta-analysis, like what are your criteria for which studies get in, and you can be sneaky with those in a way that favors your the hypothesis you want. But you can have a case where the guy who does, or girl who does the meta-analysis does it totally honestly, totally fairly, but it might just be that all the studies that got published are shit, either because publication bias, so only the ones that found an effect got published, the rest didn't, or p-hacking, so all the ones that got published were the result of p-hacking, and then even if you do the meta-analysis statistics correctly, you're doing it with bad studies. So your estimate of the real effect might therefore be bad. That's what I mean by garbage in, garbage out. So the garbage in part is the bad studies that are put into the meta-analysis.
What is your 1 sentence definition?
Of meta-analysis?
No, garbage in.
Is garbage in the key terms?
Yes.
Yeah, it's garbage in, garbage out.
Okay, I'm glad I put it there. So if the meta-analysis is using bad or p-hacked studies, the result of the meta-analysis is not reliable. So, as I say, so this is a great podcast, by the way. The two best psych-ish podcasts, I think, are Very Bad Wizards and Two Psychologists, Four Beers. They've had a few episodes where the two hosts from each collaborate. It's like a foursome. Yeah, those are always good. So in this video, or audio, I guess, they talk about ego depletion. Have I talked about ego depletion before?
Yeah.
So I think I might have mentioned. So it's just, I think I watched a video about it. Yeah. So this is the effect, the purported effect, where if you do some difficult or exhausting task, you perform less well on self-control tasks afterwards. That's basically the effect. So I'll show this, and in this audio they talk a bit about, it's a kind of narrative, but it's a narrative of a specific case where meta-analyses led us astray. Okay, so the end of that is very significant. So the researcher talking there openly admits that, prior to the replication crisis, I was using questionable research practices like p-hacking and was able to get these ego depletion effects. But post-replication crisis, I have not been able to get them. And before that, he talks about how there was a meta-analysis done with the pre-replication crisis studies, and especially if you don't include the unpublished studies, ego depletion looks good, but now it's pretty clear that either it doesn't exist or you can't get it with the standard methods that are used. So having said all that, and a lot of this is reviewed from our discussion of the replication crisis earlier, I promised some good news. I have another clip from the podcast, but we're almost out of time. If you want, I can send you the link, but one of the two hosts, Yoel Inbar, recently had someone on who made another attempt at replicating studies, all of which were kind of post reforms like pre-registration, etc. Not as big as the original. He did 14 random studies in top psychology journals. Only 2 didn't replicate. So that's a huge difference. That is consistent with my anecdotal experience in grad school in psychology. Things really have, as far as I can see, improved. And based on some other stuff, Yoel himself guesses that now probably around 90% of results are replicable. Whereas in the old days, we saw, depending on what measure you use, maybe 30, 40, 50%. I'll close with a potentially tacky quote. MLK famously said that the arc of history is long, but it bends towards justice. We can modify that. The arc of science is long, but it bends towards the truth. Science is fallible, but it does have the advantage that it tends to be self-correcting, at least in the long term. Yep.
Sorry, could you just give a final definition for meta-analysis again?
Just for meta-analysis itself? Yeah, so meta-analysis is just when you get all the studies in a given area and average them together.
And for replication?
Replication in general,
Yeah.
you take a study and you do it again.
Thank you.
Yep, no problem. Any other questions? Yep.
How would they determine what studies to use in the meta-analysis? Like you mentioned that some of the studies were like published and some were unpublished. Were they all peer-reviewed, or how would they determine?
Yeah, so you can have criteria. So if you're doing if you want only peer review, then by definition you're only doing published ones. And you look, that's not crazy. You might say, well, the ones that are peer reviewed have been vetted more carefully, but there's the publication bias issue. Usually only positive results get published. So most people would say you should include unpublished data sets too. As far as which to choose, one thing you have to decide is how similar do I want them to be? So let's say it's my IQ example. So you want to look at, okay, let's say, how big is the female advantage in verbal fluency? Well, there's different measures for verbal fluency. And if they're different enough, you might say, well, now we're almost talking about a different thing. So there's questions, and those are a matter of choice. There's no absolute rule, but you have to kind of make decisions like that.
How do you go about getting unpublished studies for a meta-analysis?
So often they're just, so look, here's one concrete example. There was a study I did at the U of A, a couple of studies, including replication, that I haven't published yet. I've kind of given up on it. The peer reviewers have pointed to some pretty important methodological flaws in the study. I won't go into the details, but the data sets are available online. You can, often there are preprints of studies, just so that the community has access to them, and also so then you can, if someone tries to publish before, you're like, no, I did do this study first. Here's the preprint.
So like in the new paradigm, it's like all that stuff is online.
Even in the old days, it was often online, but it's even more now through preprints have existed for a long time, but there's more of them available. So preprint just means you have your paper, you throw it on the internet or some other medium before it's been peer reviewed and published. And it might never get published, but it's still there for meta-analyses or for other. Or also, it's also useful because, look, you may make innocent mistakes. Like maybe you do some computer coding error and someone can look at your data set and go, oh, you made a mistake, this is the actual result. Yeah.
Just curious what the test questions are going to be.
Yeah, so that's what's next. So test questions. So as I already mentioned, next week there's no test, it's just optional test review day. I've posted an announcement about the test, but it's August 18th, 12 p.m. here in this room. Which does help slightly if you've taken it, well, all of you have taken intro psych. Being in the same context does help memory, at least somewhat.
What time did you say?
12, so noon, 12 p.m. Okay, so the two written. So I think I've hinted at both already, either today or last class, but the first one will be about factorial experiments. So the three ingredients are, you have to include a concrete example of a factorial experiment. And then you have to say what a main effect would be in the context of your made-up example. And what an interaction effect would be in the context of your made up example. And then the other written will require you to define statistical significance, practical significance, and effect size. It'll be about the relationship between those three things.
Can you see the virtual one?
Yep, so you'll have to make up your own example of a factorial experiment. And then you'll have to say what a main effect would be in that example, and what an interaction effect would be in that example. Okay, any questions? All right, I'll stick around if you're too shy and want to ask one-on-one. I'll see some of you next week and the rest of you on the test. So I've enjoyed this. If I don't see you after the test, good luck with life.
Thank you for the semester.
All right.
Thank you so much.